Hello everyone, welcome to AVLSI lecture number 11, part number 1. So today's topic is common source amplifier with source degeneration, part number 1. So let us begin. So here you can see this is my circuit for a common source amplifier, and additionally we have a resistor in the source terminal connected to the ground, right? So that's why the circuit is called as common source amplifier with source degeneration. Now, we have a microphone signal as we have seen in CS amplifier, and this microphone signal is a time varying signal, very small amplitude, and we have a V1 bias voltage to bias the M1 transistor in the saturation region. So, in presence of the signal, the current will flow and your MOSFET will be operating in the saturation region. Fine. So this circuit can be redrawn as follows. So it's understood that whenever we write V in from now on, it includes the microphone signal as well as the bias voltage. So instead of drawing it in detail, we will be drawing in short. So here we have a resistor RD, RS, and V in. V in is applied to the gate terminal. It contains the microphone signal as well as the bias voltage, and we have the output from the drain terminal. Now, let's check the biasing condition first, assuming that lambda is equal to 0. So when we apply the KVL in the gate source loop, what do we get? Here, if we apply the KVL, what do we get? V1 minus VGS minus IDRS is equal to 0. Fine, because these are DC quantities. So we can write V1 as equal to VGS plus IDRS, which is equation number 1.1. Okay, so this is the equation for V1, that is the bias voltage. It should be equal to VGS plus IDRS. Now, assuming that M1 transistor is operating in the saturation region, we can write the drain current formula as ID is equal to half mu1 Cox W by L VGS minus VTH the whole square. Okay, now V1 is the bias voltage, which will be known to us, right? Now, equation number 11.1 and 11.2, there are two unknowns, VGS and ID. So you can solve these two equations and find out the unknown values of VGS and ID. So this is about the biasing conditions for CS amplifier with source degeneration. So I'll just glance through the topic once. So we were checking the biasing conditions for lambda equal to 0. So first we found the expression for V1 in terms of VGS and ID. And we know that the unknowns over here are VGS and ID. And then in the formula for, in the expression for ID, we have again two unknowns, ID as well as VGS. So we solved this equation number 11.1 and 11.2 to find the value of VGS and ID. Okay, so this was about the biasing condition. Now let's go to small signal voltage gain and try to derive the formula for the small signal voltage gain by drawing the small signal model. Fine. Now also one more thing is there that we will assume that lambda is equal to 0 and will also ignore the body effect. Now remember here VSB is not equal to 0 for M1 transistor. But first we draw a small signal model without affecting, without considering the body effect as well as lambda is equal to 0. So we'll replace this M1 with my small signal model consisting of VGS between the gate and the source. Then we have GM into VGS connected between the drain and the source terminal. And the rest of the terminals comes from here. So at the gate terminal, we have V in. At the drain terminal, we have a resistor RD going to the ground. And at the source terminal, we have again a resistor RS going towards the ground. Now, since voltage V out is in parallel with resistor RD, we can write the current flowing through RD will be V out upon RD. Okay. Now, since the current is entering into, leaving the drain node over here, the current leaving and the current entering should be same. So here the current leaving is minus V out upon RD, and that should be equal to the this value. So here the current entering and the leaving should be same. That's why this value should be minus V out upon RD, because the direction is different. Okay, because if I consider in the other direction, it will be V out upon RD. But since the direction is opposite, here we write V out upon RD. and this current flows to the resistor also. So here also we have written minus V out upon RD. Any doubts here? You can ask. Okay. So from this analysis, a smart observation, what can we do is we can equate GM into VGS is equal to minus V out upon RD. So what will my VGS become? VGS will be minus V out upon GM into RD. We call this expression as 11.3. Now next, we applied a KVL to the gate source loop. So what do we get? We get V in is equal to VGS plus VRS, voltage across the resistor RS. Now, what is VGS over here? VGS we can write in from equation number 11.3. So V in is equal to minus V out upon GM into RD. And what is the current flowing through the resistor RS? It's minus V out upon RD. And what's the resistance? RS. So what will be VRS? Current into resistance, which will be RS into minus of V out upon RD. So that's what we are getting. And here we are clubbing the terms of V out together. So we get V in is equal to minus V out into 1 upon GM into RD plus RS upon RD. Okay, let me just slightly maximize this. Yeah. So now we take V out upon V in ratio. So that will be equal to minus of 1 upon GM plus RS into 1 upon RD. So we have taken 1 upon RD outside. Now this RD will go up and we will have the small signal voltage gain for a CS amplifier with source degeneration equal to minus RD divided by 1 upon GM plus RS. Okay. So here in the earlier common source amplifier, the RS was 0. So what would have been the gain over here? Minus GM into RD, which we have already verified, correct? So this becomes equation number 11.4, and this gain is slightly lesser as compared to your common source amplifier without any source degeneration. But at the same time, it is more stable. We will see that shortly why it is more stable. That means my device is more linear. And here you see the gain is a weak function of GM. Why? Because this is in the denominator. So even if there are changes in the GM, the significance to the gain, the contribution to the gain is very, very small, because it's the changes will be 1 upon GM value, right? So even if GM changes, the gain of the CS amplifier with source degeneration hardly changes. So in general, we can verbalize this formula as follows. We can write AV is equal to minus of resistance tied between the drain and the AC ground. Okay, so that is RD. The resistance tied between the drain and the AC ground is RD. Next we write 1 upon GM plus resistance tied between the source and the AC ground. So source and the AC ground is RS. Let's see that. Yeah. So resistance tied between the source and the AC ground. Okay. So what is the gain formula? Resistance tied between the drain and the AC ground, that is RD, divided by 1 upon GM plus resistance tied between the source and the ground, which is AC ground, that is RS. So the formula will be minus of 1 RD upon 1 upon GM plus RS, right? So in general, this is the formula. Now, so any doubts over here, how we have derived? So let me glance through the topic once. So we have started with a small signal voltage gain derivation with lambda equal to 0 and without any body effect. That's a big, assumption. But for simplification, we are starting, and we have applied the KVL and we got the result in 2 or 3 steps. And finally, my gain of CS amplifier with source degeneration was given by minus of RD divided by 1 upon GM plus RS. And it was found that this gain is slightly lesser than the CS amplifier, but it's more stable. Okay. So let's move forward now. Yeah. So there is something called as negative feedback introduced by RS. Okay. So this negative feedback is responsible for the, a slightly reduced gain, but it is also responsible for the gain stability. Now this resistor RD can be any load. Now we have studied various loads, right? We have studied current source load, resistive load, triode load, then diode connected load. So this RD can be any load, right? So once we have a negative feedback, it means we have a reduced gain, but with the advantage of having more linearity. So ideally we wish an amplifier gain to be constant and not depend on the process or the temperature variations. Okay, so let's say your ID varies with temperature. So mu n can change with temperature. So what will happen is, right now your V out expression is what? V out is given by ID into R out. Okay, the drain current into the resistance R out. That is a small signal gain, right? So as your ID increases, what will happen? V out also increases. Okay, as your ID increases, your V out also increases. But what is your VRS now? Your VRS is given by IDRS. So as your ID increases, your VRS also increases. Okay, so basically your V out is actually given by ID into R out minus VRS. Okay, that's the actual expression, right? So yeah, that's the expression over here. V out is equal to ID R out minus VRS with the inclusion of RS. Okay, now this was the formula V out equal to ID R out. That was without RS connected. Okay, just to make clear. So that time what was happening, if ID was increasing, V out was increasing. But now what happens is VRS is equal to IDRS. So if ID increases, VRS increases. And what will happen is right now the formula has become, due to source degeneration, with the inclusion of RS, V out has become ID into R out minus VRS. This means that if V out increases earlier due to ID, okay, earlier it has increased due to ID, right? So VRS will increase. And if VRS increases, your V out will drop down. So that means if my V out increases or decreases, my output correspondingly increases or decreases, maintaining its value constant. Okay, so therefore this value of RS, this resistor RS, helps in stabilizing the output voltage. Hence we get a stable gain. So we get a stable gain. That's a unique advantage of a common source amplifier with source degeneration. And also inclusion of RS have a negative effect on the gain. That is, the gain reduces. That's the disadvantage, perhaps the most important disadvantage also. So inclusion of RS also introduces body effect, which is again a problem. That means if you look carefully in this diagram, your source terminal is not connected to ground. It is in fact connected to ground via resistor RS, whereas your body terminal is connected to ground. That means if I measure VSB, it's not equal to 0. That means in the gain expression, your GMB terms will come into picture. Right now, we have not included that. We have simplified it, but really that is a nuisance and it becomes a complicated gain expression. Fine. So just for a summary, what does the advantage of common source amplifier with source degeneration? It helps, RS helps in stabilizing the output voltage, and hence we get a stable gain. Then we have a reduced gain, and also inclusion of RS will cause body effect, and which will affect all the terms, including your gain expression, your current, drain current, and everything. Now, okay, I hope that this is understood now, what really happens when we have a negative feedback in a common source amplifier with source degeneration. Okay, we have a reduced gain, but a more linear gain. Okay, so let's move on to the next topic now. Now, we will be deriving the voltage gain, small signal voltage gain, using a lemma. So what is a lemma? Sorry. A lemma is a minor result that has been proved to be true. So let us see what is this lemma. Yeah. So the lemma is that in a linear circuit, the voltage gain is equal to minus Gm into R out, where Gm denotes the transconductance of the circuit when the output is sorted to ground, and R out represents the output resistance of the circuit when the input voltage is set to ground. Okay, so what does it means is, let's say if you have an amplifier network wherein we have connected the input, so we have an output, right? So how do we represent this in a model form? We have a current source I out. In parallel, we have a resistance R out. So basically, that's a Norton's equivalent of a linear circuit. Fine. Now, how do we do the GM calculation? We do the GM calculation by short circuiting the output terminals, and we calculate I out from here. Okay, so that becomes your I out expression where V in is intact. For R out calculation, we short circuit V in and we deactivate any active V in source to 0, and then we calculate R out. Okay, so what will be GM from here? GM will be I out upon V in, right? And R out will be simply the resistance, equivalent resistance seen when V in is equal to 0, right? So what will be my gain now? Gain will be now given by minus capital GM into R out. Now this lemma will prove useful if GM and R out can be determined by inspection, not by deriving. Okay, so again I repeat, we will be deriving the gain of common source amplifier with source degeneration using a lemma, and it is very useful lemma. It says that the voltage gain is equal to minus capital GM into R out, where it has given the procedure to determine GM value. So GM can be determined by making the output terminal short and calculating I out upon V in, and then we calculate R out, and then finally we calculate the voltage gain given by minus of capital GM into R out. Okay, so let's apply this, and yeah, let's start. So let me slightly reduce this to 30. Yeah. So what do we do is we will now derive the same small signal voltage gain using lemma technique. Okay, so here is my circuit diagram. The small signal model of a degenerated CS amplifier excluding the load resistor RD. Okay, we are excluding it right now. So we have not included the load resistance over here. So we have just drawn the small signal model. Wait a second. Yeah, we have just drawn the small signal model of a degenerated CS amplifier excluding the load RD. Fine. So right now my gain of a CS amplifier is given by minus GM into RD, where RD is the load resistance and GM is the transconductance of the device. Okay. So a gain of a CS amplifier, in fact, perhaps for any amplifier, will be given by minus transconductance of the device. All the CS amplifiers, sorry. So gain of a CS amplifier will be given by minus of transconductance of the device into the load resistance, which is true for all the CS amplifier with different load. It doesn't matter. Now, what do we do is, how do we calculate the gain by expression, by inspection basically? So AV is given by minus of GM, capital GM into load resistance. Now, what is the difference between here and here? Here we have the transconductance of the device, but this capital GM is the transconductance of the amplifier, right? And this transconductance is proportional to 1 upon Rm, which is my trans resistance basically, right? And what is GM given by? GM is given by I out upon V in. And what is I out over here? I out, we short circuit the output, right? Nodes. So we get I out is equal to ID and V in. So what we have to do is, next we have to find Rm, which is the trans resistance. So trans resistance can be found by looking into the source terminal. So when you look carefully, right, when you look carefully between the gate and source, what is the impedance offered by this current source? Okay, this is a current, right? But what is the resistance offered by this? So the resistance offered by this current source will be 1 upon GM. Fine. So this 1 upon GM is nothing but my this resistor. It's effectively as a resistor, because we are linearizing the non-linear device by drawing the small signal model. Okay, so the resistance offered by this current source is 1 upon GM. So that means effectively we have two resistances in series. One is 1 upon GM and other is RS. Okay, so this together we call it as RM. So the resistance looking at the source terminal will be RS plus 1 upon GM. So Rm will be equal to 1 upon Gm plus Rs, and Gm will be 1 upon Rm. So that will be equal to Gm upon 1 plus Gm Rs. Now, what was the voltage gain, right, of the circuit? So voltage gain of the circuit was given by minus Gm into Rd. Now we bring back the value of Rd, right? Okay, from here we are, from here we have written minus Gm into R into load resistance. So Gm value we have found out, multiplied by the load resistance, and the load resistance is Rd, right? So AV will be given by minus of Gm upon 1 plus Gm into Rs. And if we take Gm common, divide both numerator and denominator by Gm, we get AV is equal to AV of CS amplifier with source degeneration will be equal to minus of Rd divided by 1 upon Gm plus Rs, and which is the same formula as we have arrived, as we have derived earlier, right? And this is assuming that lambda is equal to 0 and the body effect is ignored. Okay, and that's a very crude assumption basically. Body effect shouldn't be ignored, but here just for simplicity and the use of the lemma, we are using this. So this technique of finding the gain greatly simplifies the analysis of more complex circuits, like for example differential amplifiers or op-amp. So what do we do? Well, let us revise. So what have we done? We know the gain of the small signal amplifier will be given by minus Gm minus capital Gm into R out. So we calculate R out. R out is Rd only over here, and capital Gm is calculated as follows. Gm was proportional to 1 upon Rm, and Rm was effectively Rs plus 1 upon Gm. Now we got the value of Gm. We plug in the values in the gain formula AV. So finally we got the small signal voltage gain of a CS amplifier with source degeneration, which is coming out to be same as we have derived earlier and using the lemma. Okay, so this lemma will be very useful when we derive the same expression for the voltage gain while assuming the body effect is not ignored. Okay, so yeah, I think we have come to the end of this session, and so far we have learned how to use a lemma, and we have seen what is the effect of the negative feedback, and also we have derived in general form the small signal voltage gain, and also we have touched the biasing condition for the common source amplifier with source degeneration. Okay, so next time we will continue with this topic and try to derive the voltage gain formula with body effect. So until then, have a good day and thank you.